Welcome back to the deep dive. Today, we're diving into, well, the real basics of how things move. It's called kinematics in physics.
That's right. We've gathered a whole bunch of material, and our goal is pretty straightforward. Boil it down to the absolute essentials.
Things like speed, velocity, acceleration, and gravity. We want to give you a really solid grip on the language scientists use to talk about motion.
Exactly. It's about moving beyond just saying something's fast. We need the precision Galileo started aiming for.
Understanding the difference between just how fast you're going and, crucially, where you're headed.
If you get these core ideas, especially vectors, you're laying the groundwork for understanding almost everything physical, from, dropping your keys to planets orbiting the sun.
Okay, so to kick things off and show why this precision really matters, let's throw out a bit of a puzzle.
I like puzzles.
Imagine you're driving. You're going in a perfect circle, maybe on a big roundabout, and your speedometer. It's absolutely steady. Let's say 60 kilometers an hour, dead on.
Okay, constant speed.
Right. The question is, are you accelerating? Instinct kind of says, no, right, speed isn't changing.
But physics has a different answer.
A very definite yes. And figuring out why that's a yes is a big part of what we're unpacking today. All right, let's start simple. The most basic concept, speed.
Yep. At its heart, speed is just how much distance you cover divided by how long it took you. Pure pace.
And we should probably give a nod to Galileo here.
Oh, absolutely. Before him, it was mostly just faster or slower. He was the one who started thinking, okay, how can we measure this?
His big idea was measuring the distance covered in equal chunks of time, right?
Exact. That mathematical definition was revolutionary.
Now, when we talk speed day to day, or even in physics, there are actually two types we often mean. First up is average speed.
That's your road trip calculation. You drove, say, 320 kilometers.
Okay.
And it took you exactly 4 hours, including stops for coffee or whatever.
Right.
Your average speed is just the total distance, 320 kilometers, divided by the total time, 4 hours, which gives you
80 kilometers per hour. Simple enough.
But that 80 kilometers per hour, well, it hides a lot. It doesn't tell you if you were crawling in traffic for an hour and then speeding later.
No, it's just the overall average, which is why we also need instantaneous speed.
Precisely. That's the speed you have at any single moment in time.
Like what your car's speedometer is showing you right now.
That exact number. Flickering up and down, maybe, that's instantaneous speed.
Okay, so speed is straightforward. Just a number telling us how fast. But then physics introduces something that sounds similar but is way more descriptive. Velocity.
Ah, yes, velocity. This is where things get, let's say, more specific and more powerful.
Because velocity isn't just about how fast.
Nope. Velocity needs something extra. It must include direction.
Okay, and this is the whole scalar versus vector thing.
Exactly. It's a fundamental distinction. Speed is a scalar.
Meaning
Meaning it just needs a magnitude, a number to be complete. 60 kilometers per hour. That's speed, a scalar value.
Got it. Tells me how fast, but not which way.
Precisely. Velocity, on the other hand, is a vector. And vectors always need two things, magnitude and direction.
So not just 60 kilometers per hour, but
60 kilometers per hour north or east or 30 degrees west of south. That direction component is essential.
And why does that direction matter so much? People mix these up all the time.
Because knowing the direction lets you predict where something will be. It lets you track motion accurately. If I just tell you my speed, you don't know if I'm getting closer or farther away.
But if you tell me your velocity,
Then you know both how fast I'm moving and the path I'm taking. That difference is absolutely critical for everything that follows, especially acceleration.
okay, so if velocity tells us speed and direction, then acceleration. This is about changing that velocity, right?
Exactly. Acceleration is defined very precisely as the rate at which velocity changes. Any change in velocity counts as acceleration.
And because velocity has those two parts, speed and direction, that means there are two ways you can accelerate.
Precisely two ways. The first one is the one everyone gets intuitively.
Stepping on the gas or hitting the brakes. Changing your speed?
Right. Speeding up is positive acceleration. Slowing down, well, that's negative acceleration, sometimes called deceleration.
Makes sense. But the second way?
The second way is changing your direction. And this brings us right back to that car in a circle.
Ah, the puzzle.
The speedometer reads a constant 60-kilometer area. Speed isn't changing.
But the direction is changing every single instant you're turning that wheel.
Yes. And because the direction is changing, the velocity vector is changing.
And if the velocity is changing?
Then by definition, you are accelerating. even with constant speed.
Okay, hold on. That still feels a bit weird. If my speed isn't changing, where is the oomph for this acceleration coming from? I feel pushed outwards in the seat when I turn. Is the acceleration outwards?
That's a brilliant question because it gets right at the forces involved.
Yeah.
What you feel pushing you outwards isn't really a force pushing you out, it's inertia. It's your body wanting to keep going straight. That's the actual force causing the acceleration, the one making you follow the curve, is directed inwards, towards the center of the circle.
Inwards, like the tires gripping the road.
Exactly. The friction between your tires and the road provides that inward force. We call the resulting acceleration centripetal acceleration center seeking. That force is constantly redirecting your velocity vector.
Wow, okay. So the feeling is outward inertia, but the actual accelerating force is inward. That clears it up. The vector is rotating even if its length, the speed, stays the same.
You've got it. And we measure this rate of change. Acceleration is the change in velocity divided by the time it took for that change to happen.
The units get a bit funny sometimes, like in that example from the sources. A car goes from 60 kilometers to 90 kilometers. That's a change of 30 kilometers.
Right. And let's say it does that in 2.5 seconds.
So 30 divided by 2.5, that's 12. The acceleration is 12 kilometers per hour per second.
It sounds awkward, but yes. It means for every second that passes, the car's speed increases by an additional 12 kilometers per hour.
But usually we use meters per second squared, right? Text
Yeah.
2 2.
That's the standard scientific unit, yes. Meters per second per second. And that's the unit we always use when talking about the most famous source of constant acceleration.
Gravity.
Absolutely gravity. And again, we circle back to Galileo. He had this problem. Things fall really fast.
Too fast to measure accurately back then.
Exactly. He didn't have stopwatches or high-speed cameras. So direct observation wasn't going to cut it for figuring out the details of how things fall.
So what did he do? This is the clever part, right? The ramps.
The inclined planes.
Yeah.
Pure genius. He realized that rolling a ball down a gentle slope was like watching gravity work in slow motion.
It dilutes the effect of gravity, sort of stretches it out over time.
Precisely. It allowed him to use simple water clocks, or even his pulse, to measure the time it took for the ball to cover different distances down the ramp.
And what did he find?
He found that the distance covered was proportional to the square of the time, which mathematically points to one thing. Objects don't fall at a constant speed. They fall with constant acceleration.
And when that constant acceleration is only due to Earth's gravity, with nothing else interfering.
We call that free fall.
Which brings us to that magic number everyone studying physics bumps into.
Yep. The acceleration due to gravity, symbolized by g, is about 9.88 centimeters per second squared, on average, near the Earth's surface.
Though often in problems, like in our sources, they round it up for simplicity.
Right, they often use $10 text MS22 just to make the math easier to follow. It's close enough for many examples.
Okay, let's make that $10 TXMS22 really concrete. If I drop a rock from rest, what does that number mean for its speed?
It means that for every second it falls, its speed increases by 10 meters per second.
So start at 0 speed at time 0.
After 1 second, it's falling at 10 meters.
After 2 seconds?
20 meters. After 3 seconds, 30 meters, and so on. It just keeps adding 10 meters every second,
Assuming no air resistance.
assuming no air resistance, which is a huge if in the real world, especially for light things.
Yeah, this is where the classic feather versus bowling ball question comes in. My gut tells me the bowling ball wins that race every time.
And in the air, it does. Because air resistance has a much bigger effect on the feather. It depends on shape and speed, not just mass.
But if we could get rid of the air, like in a vacuum chamber.
In a perfect vacuum, Galileo's principle holds true. Gravity pulls on everything the same way, regardless of mass. So that feather and the bowling ball.
They'd fall side by side, accelerating at exactly $10 tex MS22, and hit the ground at the exact same time.
Experiments have shown it time and time again. It's one of the beautiful, non-intuitive truths of physics. Mass determines the gravitational force, but not the resulting acceleration in free fall.
Okay, and this downward acceleration of 10 meters squared, it's always acting, right? Even if something is moving upwards.
Always. Think about throwing a ball straight up. As it rises, gravity is constantly pulling down, slowing its upward velocity,
Until it reaches the very top of its path.
where its instantaneous velocity is 0, just for a moment.
But even in that split second of 0 velocity,
It is still accelerating downwards at $10 TXMAJ02. The acceleration never stops. It's constantly changing the velocity, slowing it on the way up, zeroing it at the peak, and speeding it up on the way down.
So we've hammered home that velocity and acceleration are vectors. They have direction. How does that play out when things get more complex, like in the real world where multiple things might be affecting motion at once?
That's where vector addition becomes absolutely essential. Almost nothing moves due to just one single influence.
Right. Like if I push a heavy box and you help me push.
We can't just add the amount to push unless we're pushing in the exact same direction. If I'm pushing north and you're pushing east.
The box isn't going to go just north or just east. It'll go somewhere northeast-ish.
Exactly. We have to combine those force vectors, usually using geometry, like drawing arrows head to tail or using the parallelogram rule.
To find the single resultant vector that represents the actual motion, or the net force.
That resultant vector tells you the true outcome, the actual direction and the actual magnitude, whether it's force, velocity, or acceleration.
Our sources had a really good classic example of this, the airplane flying in wind.
Yes, perfect illustration. Pilots deal with this constantly. Imagine a plane trying to fly due north.
Okay, its engine pushes it north at, say, 100 kilometers per hour relative to the air around it.
But there's a crosswind blowing strongly from the west towards the east. Let's say it's 60 kilometers per hour.
So the air itself is moving sideways while the plane tries to move forward through it.
The plane has a velocity vector of 100 kilometers north relative to the air, and the air has a velocity vector of 60 kilometers east relative to the ground.
The plane gets pushed north by its engines, and pushed east by the wind simultaneously.
So its actual path over the ground isn't north. You add those two vectors, 100 north and 60 east, draw the rectangle.
The actual path is the diagonal of that rectangle, pointing northeast.
Correct. And using Pythagoras, the actual speed over the ground, the magnitude of that resultant vector, is the square root of 100 squared plus 60 squared, which is about 117 kilometer.
So it ends up going faster than its airspeed indicator says, and it ends up way off course to the east if the pilot doesn't compensate.
Precisely. They have to aim somewhat west of north to actually travel north over the ground. It shows why just looking at your speed isn't enough. You have to account for all the velocity vectors acting on you. Hashtag outro.
Well, that feels like a pretty thorough tour of the absolute fundamentals. We've seen why precise words like speed, velocity, and acceleration are so crucial.
Yeah, speed just tells you how fast you're covering ground. But velocity adds direction. And acceleration describes any change in that velocity, speeding up, slowing down, or just turning.
They're the building blocks for describing pretty much any motion in the universe.
It was really good revisiting this. And credit where it's due, the sources we looked at, like the materials often attributed to educators like H.V. Torin, really lay this out clearly. That structured approach is so important for learning physics.
Absolutely. Okay. Before we wrap up, let's leave our listeners with something to chew on, something that connects back to all this motion stuff.
Sounds good.
Think about this. You jump straight up in the air, you come straight back down to the same spot, right?
Uh-huh. Ignoring tiny drifts, maybe, but basically, yes.
Okay, now remember, the Earth isn't stationary. It's spinning on its axis, and it's orbiting the sun at a truly insane speed, something like 30 kilometers per second. That's over 100,000 kilometers per hour.
Wow, yeah. Hard to even picture.
So when you jump, why don't you get left behind? Why doesn't the Earth just zoom out from under you at 100,000 kilometers per hour, slamming you into the wall behind you? What does the fact that you, the air around you, and the ground all move together perfectly despite this incredible underlying speed tell you about motion itself, about your frame of reference, about inertia?
That's a great one. It forces you to think about relative motion and the fact that we're already moving with the Earth.
Something to ponder. Thanks for joining us on The Deep Dive.